Hello everybody, back with semiconductors physics second year topic Riju and PSK classes. We were doing semiconductors and we studied about diodes, forward bias and reverse bias of diode. Okay, so today we will be doing some numericals in the beginning so that the idea of forward bias and reverse bias become more clear, and we will also learn how to approach them, approach problems with these ideas. Okay. See the very first question on the board. In the figure given, voltage of point A. Voltage means the potential at point A. And you must be familiar about this symbol. This symbol say it is connected to the ground, and ground always is taken at zero potential. And the other side of the diode is given a potential minus 3 volt. So one side is minus 3 volt, other side is close to 0. Is this forward bias or reverse bias? For forward bias, we studied that the P side, this side should be at a higher potential than the other side. If P is at a lower potential than the other side, this is reverse bias. So is it forward bias? Is it reverse bias? Work out like this one. Right side you consider 0, left side you consider minus. So this is negative, that is more, that is 0. So we can say this is at a lower potential than that side. So the P side is at a lower potential, the N side is at a higher potential. This is reverse biased. Will it conduct? In the reverse bias, the conduction is very small. You can say there is no current practically. The resistance is infinity, very high. So there will be no current flowing through the diode, and there is no current flowing through the resistor. If there is no current flowing through the resistor, then you should know both the sides are at the same potential. This side and that side are at the same potential. There is no connection here. See, when it is not conducting, there is no connection between the resistor and this minus 3 volt. So this minus 3 is not available. But you can see the resistor has got 0 potential on this side because this is connected to the ground. So point A also has 0 potential. The potential at A must be equal to 0 volt. Answer is 0 volt. Now tell me, can you explain this? If you can explain this, it's good. So if you can explain it here, you can apply this somewhere else. Okay. Let's go to the next one. Same idea, same strategy. Calculate current I, it's marked here, current I, that is the current coming from the cell. If all the diodes are ideal, diode ideal means what to do? If diode is ideal, forward resistance is 0, reverse resistance is infinity. Forward resistance 0, reverse resistance is infinity. That means if a diode is forward bias, you can consider it as a short circuit one. And if it is a reverse bias, you can consider it as an open circuited one. Now, the potential difference given is 200 volt. That makes this side at a higher potential and this side at a lower potential 0. Look at each of the diode. Look at this diode. Look at this diode. Its P side is at 0 and the N side must be at a higher potential. So, this one, its P side is at a lower potential, N side is at a higher potential. Is it reverse biased or forward biased? It is reverse biased. So there will be no current flowing through this branch. It will not conduct. Now look at this diode. Its P side is here. It is at a higher potential and N side is at a lower potential. That is forward biased. It's an ideal diode forward biased. Means what to do? Consider this is connected directly. That means you need to consider only the resistor there. You don't have to worry about the diode because ideal diode means its resistance must be taken as 0. What about the diode on the top? The diode on the top, you can see that its N side is connected to plus 200. So that is reverse biased. So that will also not conduct. So the circuit become very simple for us. The circuit become very simple for us. The circuit will actually, practically the circuit will look like a, I'll just draw. I said this battery is connected. This is a battery connected, and I said this diode will not conduct. this will also not conduct. So when there is no conduction, you don't have to worry about that circuit. Okay, so that means whichever is conducting, this will conduct, and if it is conducting, you can consider it as a direct connection because you are replacing the diode with its forward resistance. And what is the forward resistance? It's being ideal, you take it to be 0. Then the only resistor that you have is here. So current will flow. This is 200 volt connected. And what is the value of each resistor? Each resistor is 200 ohm. So the circuit very simple. It's very simple, though it appears to be complicated there. And if you connect only the conducting part, it will be only this much. And what is the current? That should be 200 volt by 200 ohm, 1 ampere. The answer is 1 ampere. Now tell me how to explain that the answer is 1 ampere to someone, a third party. Try to explain this to somebody else. How do we explain this? If you can explain it, you can apply it. Oh my God, that's a very good statement, right? If you can explain it, you can apply it somewhere. I'm great. This is quite complicated, directly related to current electricity. Read question carefully, patiently. A potential difference of 2.5 volt is applied across the faces of a germanium crystal plate. It is only a germanium crystal plate, it is not a diode. It's only a semiconductor, a piece of semiconductor, and it's germanium. It is germanium. It is not given whether it is doped or not. So if it is not given, we will consider it as a pure germanium. Pure germanium, that's an intrinsic semiconductor, where the number of electron and hole will be always equal. The phase area of the crystal is given, its thickness is given, the free electron concentration in germanium is given, and the electron and holes mobility, ability to move is mobility is given. The current across the plate will be, you need to calculate the current. Okay, this is actually easy. This has nothing to do with much with the semiconductors. Okay. So consider that this is the semiconductor block. Okay, you can say the phase area here is given as 1 centimeter square. That is the area of this phase. Fine. Now the thickness is 1 millimeter. This thickness is 1 millimeter. Potential difference of 2.5 is applied. Where is it applied? Across the faces. Faces means this is one face and there is one face behind that one. So you are applying that potential difference across the face. That means there is a connection coming from the back side. Okay, I'll mark it here. There is a connection coming from the back side and there is a connection given to this side. Here you are applying a potential difference. And this is 2.5 volt. Okay, in another way I can say, if I consider this as the germanium plate, this is one face, this is the other face, and I am applying a potential difference like this. Okay, this becomes the thickness. This is thickness 1 millimeter. This is 1 millimeter. This is 2.5 volt. Okay, now a current will go from the cell back to the cell, and that will go through the semiconductor. And semiconductor, you know, not like a metal. There are two types of currents here. One is the electron current, another is the Hall current. You studied that both of them will be in the same direction. So the total current here is nothing but the electron current plus the Hall current. Okay, so I gave you the idea of the connection and the equation required. Okay, now what? Now what? How to find current? Carefully see this. Current in such cases is given by number density into area through which current flows into drift speed into charge of the carrier. NAVD, direct equation from current electricity. But see, VD, drift speed is not given here, but mobility is given. So use the equation that mobility mu is nothing but drift speed divided by electric field, which gives you drift speed equal to mu into electric field. But electric field is not given, but the potential difference is given. So use the idea, electric field is equal to potential difference by the length or the thickness, by length. Right. What is that length? It is the length through which current is flowing, and that is the thickness of the slab here in this case. Okay, so combining all this, I can write the equation of current as number density into, see here number density area, here, okay, let me write like this, NA into, instead of VD I can write, I put E here, then I'll write VD. VD is nothing but mu into E, E is V by L, so this will become mu into V divided by L. But I told you there are two currents, one is due to electron, another is due to hole. And for electron and hole, this N and mu will be different. So what is common for both electron and hole? For both electron and hole, area will be the same, charge of the particle, whether it is hole or electron, charge is same. Okay, then the applied voltage is same, and the length through which the current flowing is same. Clear? So I have taken A, E, V, L, then mu into N. This is the equation that I am going to use. I equal to A, E, V by L mu into N. A is the area of the cross section, E is the charge of the carrier particle, electron or hole, V is the potential difference applied, L is the length through which current flows, that is actually the thickness of the plate in this case, mu is mobility, N is the number density, all the parameters are given. Now we have to go for the idea that the current here is due to both electron and hole. So you have to write this equation twice for both of them. But this is a germanium crystal, so we will consider it as a pure semiconductor. So if it is pure, number density of electron equal to number density of hole. So that makes my equation more simpler, because in that case I can say this number density also become common and only the mobility will be different. So writing the equation, this should be written for electron, this should be written for hole. So what is the final equation? See this one, I equal to, all these parameters are common, that is A into E into potential difference into number density divided by length is common, but the only thing different is that mobility of electron plus mobility of the hole. That is the final equation. Now just substitute values and calculate. Okay, so this is the major equation. You have to write this for electron. If you are writing for electron, what should I write? I due to electron equal to A, E, V, N due to electron, mu of electron. Now if I am writing this for the hole, then this E should be replaced by hole, this should be replaced by number density of hole, this should be replaced by mobility of the hole. But in this case, Ne and NH are equal because this is a pure semiconductor, because nothing is given about doping. Some data was given, only then we can think otherwise, but here you can't. So this is the equation. Now let us evaluate it. Let us substitute the values. So what is the current I? I equal to A. What is the area of the cross section? That is 1 centimeter square, which will give you 10 to the power minus 4 meter square. Charge of the electron is into 1.6 into 10 to the power minus 19 into potential difference applied is 2.5 into number density is given as 2 into 10 to the power 19 bracket mu E plus mu H, it's given 0.33 SI unit, 0.33 plus 0.17, 0.33 plus 0.17 divided by length is the thickness is 10 to the power minus 3 meter. Okay, I think this calculation is pretty cool. 10 to the power minus 3, cancel this to 10 to the power minus 1. 10 to the power 19 will cancel 10 raised to minus 19. 0.33 plus 0.17 will give you 0.5. 0.5 into 2 gives you 1. So effectively what I am left out is 10 to the power minus 1 times, this 10 raised to minus 1 times, this 1.6 times, that 2.5. Okay, and this should be giving you 4 into 10 raised to minus 1. 1.6 into 2.5 is 4. 4 into 10 raised to minus 1. As per option, you can write like 0.4 ampere. So your answer is option 2. A very good question. We have to practice a lot. Okay, mobility, drift speed, all these ideas can come in semiconductors. Whatever you studied in the beginning of current electricity about the drift speed, all those things can be asked in semiconductor in this format. So this should be trained. This is purely theoretical and logical. A semiconductor X, you can see X and Y are semiconductors connected to a battery. Semiconductor X is made by doping a germanium crystal. This is basically a germanium crystal, but it is doped by arsenic. You studied this, arsenic. Arsenic is a pentavalent atom. It's an impurity atom. If you dope germanium or silicon with arsenic, you are getting an N-type semiconductor. So X is N-type semiconductor. Okay. A second semiconductor Y is made by doping, read this, germanium with the indium. Indium is a trivalent impurity. If you dope silicon or germanium with indium, you will get a P-type semiconductor. So here Y is P-type semiconductor. So it forms a junction. Now this is a P-N junction. So Y is P, X is N. That is the option that you want. X is P-type, not correct. X is N-type, it is correct. X is P-type, wrong. X is N-type. So it's either 2 or 4. Now Y is P-type, Y is, so it's either 2 or 4. Now see, is it forward or reverse bias? This is P-type. For forward bias, P-type should be at a higher potential, but here P-type is at a lower potential and N-type is at a higher potential. So this is the case of reverse bias. So option X is N-type, Y is P-type, and the junction is reverse biased. Alright. Now again comes the same idea. What is it? All the diodes are ideal. Now I will not tell what ideal diode is. The current flowing in 2 ohm resistor. Which is the 2 ohm resistor? Here 2 ohm resistor connected between diode D1 and D2 is, what is the current? You have to just look at the circuit and try to simplify it by using the idea of forward and reverse bias. Is there any diode which is forward biased? Of course. Positive 10 is connected here. So this is forward biased. Positive 10 is connected here. This is forward biased. Okay. What about this diode D2? D2 has got its N side at a lower potential. N side lower potential means that is also forward biased. So D1, D2 and D3 are forward biased. Okay. Because to forward bias a diode you need something around 0.6 volts. So we are giving 10 volts. So even when they share it, enough voltage is available for D2 for forward bias. What about D4? D4, the P side is at a lower potential and N side will be probably at a higher potential. So D4 is reverse biased. So D4 will not conduct. If D4 does not conduct, can D3 conduct? No. D3 can conduct, but provided there is a closed path, but here D4 will act like an open circuit. So there will be no current through D3. So D3 will have no current, D4 will have no current, 7 ohm and 5 ohm will have no current. But 4 ohm is not connected to any diode, so that will be always conduct. D1 will conduct, D2 will conduct, D1 will conduct, D2 will conduct, so there will be current through this one. Now what we can do is that we can redraw the circuit using all these ideas. So when I redraw that one, this is the circuit that we have. 1 ohm, so those diodes were replaced by 0 resistances. So 1, 2, 1, 4 ohm are in parallel, will give you 2 ohm, and that 2 and 3 are in series, will give you 5 ohm. What is asked? The current flowing in 2 ohm resistor. You want the current flowing in 2 ohm resistor. Fine. Now I can say you must have calculated the current coming from the cell. What is the current coming from the cell? That's what I want. Okay. You can see that 1, 2 and 1 are in series. So that will give you 4 ohm. This 4 and this 4 are in parallel. So that will give you 2 ohm. And that 2 ohm and this 3 ohm are in series. That will give you 5 ohm. So effectively you have a cell connected to 5 ohm. That's very easy. That means from the cell, how much current will come? 2 ampere will come. From the cell 2 ampere will come. So that current will reach this junction, 2 ampere. And for this current, there is a branch with 4 ohm resistance and there is another branch also with 4 ohm resistance. So what will happen to that current? The current will split into 2 equal currents. Why is it equal? Because the resistances are equal, same. So current in the first branch, this one will be 1 ampere and current here will also be equal to 1 ampere. So this 1 ampere will flow through 2 ohm. So question is that the current through 2 ohm should be equal to 1 ampere. This is your right answer. I hope this is also okay. Aha, same thing. Okay, no words. You don't need a pen. You can simply look at the diagram and visualize the thing and get answer. I will say, oh, I understood. Okay, D1 is reverse bias, right? And D2 is forward bias. So there will be no current through the 3 ohm. 2 ohm and 2 ohm will be in series. So 10 by 4. 2.5 ampere is the current coming from the cell. You want current flowing through R1, so current from the cell and current in 2 ohm will be equal, so that will be 10 divided by 4, 2.5. 10 by 4, 2.5. If you want to understand, this is the actual diagram. This is the effective diagram. You see, this is a real thing, but this is the effective thing. R1 and R3 are in series and the current from the cell will go through 2 ohm. Okay. Again, same thing. But this time the structure is a bit different, that's it. Consider the junction diode as ideal. Value of current flowing through AB. See, you might be having doubts. Why are you talking only about ideal diode? Why not practical diode? That will come later. There is no big deal with a real resistance diode, because if there is a resistance in the diode, then you have to use that in the circuit, that's all. Ideal means you use 0. Value of the current flowing through AB. What do you want the current from? You know, this is plus 4 higher potential, minus 6 lower potential, P side higher, N side lower, forward bias conducting. If it is conducting, there is a resistance 1K, you need to know the potential difference. What is potential difference between A and B? VAB equal to VA minus VB. See, you don't need this mathematics, you can simply visualize and get the answer, but I will say the potential difference VAB is nothing but potential at A minus potential at B. What is potential at A? It is 4 minus, what is potential at B? Minus 6. This will give you 10 volt. And what is the current through AB? Current through AB is nothing but potential difference between AB divided by resistance between A and B. And that is nothing but 10 divided by 1K means 1000. 1K means 1000. So this will give you 1 by 100 ampere. And look at the option, it's all written as power of 10. So this is 10 to the power minus 2 ampere. 10 to the power minus 2 ampere. Option 3. I am sure that with this many questions done, the concept of forward and reverse bias is clear now. And this is how questions will come about diode in circuits. All diode circuits basically belongs to current electricity circuits. Okay. Now we will go back and discuss rectifier, which we started in the last class. As I told in the last class, rectifier is a device, an electronic device, okay, which will convert alternating current into direct current. Okay. Now there are two types of rectifiers. One is called full wave rectifier, other is called half wave rectifier. Half wave rectifier, which will convert only one half of the AC, and full wave rectifier will convert both half of the AC. Okay, don't worry, you will understand this. The meaning of half and full you will understand. Okay. First of all, we have a half wave rectifier. Okay. First of all, title is PN junction diode as half wave rectifier. Half wave, not waver, wave rectifier. What is the principle? First of all, principle. Principle is simple. A diode will conduct only when it is forward biased. Reverse bias current is negligible. That is the principle. It works on the principle that the diode conducts only in forward bias. In reverse bias, you don't have to mind the small current. Now, what is the construction? They will ask in the exam, what is the construction? Construction is this. What is this? This device is called transformer. You studied. There is a primary winding, there is a secondary winding. Primary is connected to an alternating supply. An alternating supply will produce an alternating current here. Flux will change, and that flux will be linked with the secondary, and an alternating EMF will be induced in the secondary. Depending on the number of turns, you can get more voltage or less voltage. Normally, in such cases, you use a step down transformer where the output voltage will be less. Okay. because electronic circuits does not require very high voltage. They require voltage like 12 volt, 24 volt, etc. But the supply that you're getting at your house is 220 volt, so you need to step this down first. Now see the secondary. The transformer secondary has got two wires here, a coil with the two ends. One end is connected through a diode, and after that will go through a resistor here and back to this thing. This is a circuit in the output circuit. And this RL, what is RL? RL, L stands for load. Okay. The load resistance. Load resistance means that represents any device that you connect. Like if it is your mobile phone you are connecting, then this RL will represent that device. Suppose you are using a bulb here, then RL stands for that bulb. RL is the resistance that is connected to the circuit. Okay. Now this is a structure. So it consists of a diode connected in series to the load resistor in the secondary of a step down transformer. Output is taken across the load resistance. Output, the required voltage is taken between X and Y. Okay. Now you need to study the working of this. Okay, I'll tell you what it is. Working. It's very simple. Okay. This is the input voltage available. Where? This primary means you are giving an AC. Okay. In the primary, listen carefully. In the primary, you give a very big AC. I'm sorry. In the primary side, you give a very large voltage of AC. And the secondary side, what will happen? The same voltage. See, this is what we call as one cycle. The cycle and the time period will remain same, but the value, the amplitude will decrease. This is what we call step down voltage. In domestically, we get an AC with a frequency of 50 hertz. 50 cycle in 1 second. So this is 50 cycle in 1 second. This is also 50 cycle in 1 second. Transformer will never change frequency. It changes only the voltage level. 230 can be changed to 10 volt. This is available here between these 2 points, A and B. Between A and B, you get an alternating voltage. What does it mean? It means that, okay, here you can see in the first half cycle here, in the first half cycle, it means in this first half cycle, this is called first half cycle, A will be positive. You can assume like that. In the first half cycle, A may become positive or it can be negative. It can be both. But for simplicity, I am assuming that if in the first half cycle A is positive, then B will be negative. As long as you are in the first half cycle here, that is the case. A will be at a higher potential, B will be at a lower potential. Now, in the second half cycle here, what will happen? In the second half cycle, A will become negative and B will become positive. Whatever A was, now it will reverse. So during the next half cycle, A is negative, B is positive. Again, the third half cycle here, again A become positive and B become negative. So it keep on changing. Is it okay now? So if A is positive in the first half cycle, B is negative. If A is negative in the first half cycle, then B is positive. That is it. Okay. Now, what will happen? Assume that A was positive and B was negative. Look at the diode. Look at the diode. Is it forward bias or reverse bias? P side higher potential, N side lower potential. So this is forward bias. So we can say in this half cycle, diode is forward biased. Here. Now, next half cycle. When the next half cycle comes, what happens? A become negative, B become positive. So what will happen? This is a diode with a reverse bias. So we can say this is reverse biased. Again, in this half cycle, the diode is forward. In this one, it is reverse. And the forward one will conduct, reverse one will not conduct. Right. So what will happen? Now I think you understood the working. Now I'll tell you the explanation. If A is positive and B is negative in the first half cycle, diode will be conducting. And when diode conducts, the current will flow from X to Y. When current flow through X to Y, that will be a current which is varying, increasing and decreasing current. And that current will produce a proportional voltage across the resistor, because the voltage across the load resistor will be equal to I into RL. If I is an increasing current, then voltage will also increase. When I decreases, voltage will also decrease. As the input voltage increases, the current will increase. As the current increases, the output voltage will also increase like this. So you get this much voltage here. What will happen in the reverse bias? When this is negative and this is positive, diode will not conduct. When diode does not conduct, current through this will become 0 and the voltage will also become 0. So you will get 0 voltage. Again, when A becomes positive, you get the same thing. So this is the current or the voltage across the load. Even when the current in the transformer reverses direction, the current through X and Y will remain same, only one direction. So this is an alternating current, but this is only flowing in one direction. It doesn't look exactly like a steady current. This is a pulsating DC. It's changing, and somewhere in between it is 0. So this is how a half wave rectifier works. In the next class, we will discuss more details about this one with waveform, everything. So see you till then. Bye.